Hello. In this video I will briefly explain the concept of linear combination. It's the concept which really lies at the very heart of the linear algebra and geometry, an extremely important concept, and this is probably your first meeting with the concept. So I will do my best to illustrate it both geometrically and arithmetically, and I hope that you during this course will understand this concept and why it is so important. Let's start. Linear combinations. So I will begin geometrically, just to, show you the intuition behind the concept. Let's say that we have two vectors, u and v. It doesn't matter really if they are in the plane or in the space, but now I mean that they are geometrical vectors, so they are either in R2 or in R3. We can add those two vectors, right, by the parallelogram rule, and in this way you get u plus v. And u plus v, it's the very first and probably one of the simplest examples of the linear combination of vectors u and v. Simply their sum is an example, our first example of a linear combination. But you can make other linear combinations. For this you need two scalars. Let's say that I take scalars c1 equal to 1/2 and c2 equal to 1/3. Then I can produce two new vectors from my v and u. First I produce c1 times u, so it's 1/2 of vector u, and you know by now that it's the vector which is has the same direction, looks in the same direction as u, and its length is a half of the length of vector u. And c2 times v, it's 1/3 of vector v. So it's a vector which looks in the same direction as v, but its length is just 1/3 of the length of v. So just 1/3 of this entire length. And now I can add those two vectors, 1/2 of u and 1/3 of v. So this vector w, I can call it w here, the diagonal of this parallelogram here, is the vector c1 times u plus c2 times v. In this case, c1 is 1/2 of c, and c2 is 1/3. It is another example of a linear combination of our vectors u and v. So a linear combination of two vectors is just some scalar times the first one plus some other scalar times the second one. All those vectors, because you understand that if I take a scalar times vector plus another scalar times another vector, then I will get a new vector as a result. This is a linear combination of vectors u and v. So now in particular, think about the following situation. If we think that we have the origin here, then we can obtain this entire parallelogram spanned on the vectors u and v by performing those linear combinations with the constants, with the coefficients c1 and c2 between 0 and 1. Why? Well, because if we take that they are larger than 0, means that we get all the vectors which look at the same direction as vectors u and v, and when the constants, the coefficients, are less than 1, this means that the vectors will be shorter. This c1 u and c2 v will be shorter than u and v. So when we add them, we will just get somewhere inside this large parallelogram, because this point corresponds to c1 and c2 both at the same time equal to 1. This point corresponds to C2 equal to 1 and C1 equal to 0, because it's simply 1 times V. So C2 equal to 1 and C1 is 0. And these points correspond to C1 equal to 1 and C2 equal to 0. So we get this parallelogram. So each point of this parallelogram can be obtained in this way. So let's, for example, take this point inside the parallelogram. So how do we find the constants C1 and C2 for this particular point? Well, we have to draw lines parallel to the vectors V and U and see where they intersect our vectors U and V. So here this looks like, what do I know, something slightly larger than 1/2, and this looks like almost exactly 1/2, right? So you get the coefficients C1 and C2. And we can say that these two vectors generate the entire parallelogram by means of linear combinations with the coefficients between 0 and 1. And now, what happens if we take, for example, C1 equal to 0 and C2 equal to 3/2? C1 equal to 0 means that this vector U does not participate in the production of the vector W, right? And C2 equal to 3/2 means that this vector V will be 50% longer, right? So we get this vector here. And now it is also possible to take negative coefficients. So let's take this example when C1 is equal to 1/2 and C2 is negative 1/3. So negative 1/3 V will be exactly as long as 1/3 V, but we look at the opposite in the opposite direction. And and we have to add this minus 1/3 V and 1/2 U. So then we simply close the parallelogram, and this is our vector W, which is this linear combination of U and V. And you see that we, by taking negative coefficient, we got outside this parallelogram, which is spent on vectors U and V. And if we take another example, if we take both constants negative, then we, now it's better to lift the entire situation. So we get minus 1/2 U is the opposite of 1/2 U, and minus 1/3 V is the opposite of plus 1/3 V. And again, closing the parallelogram gives us this resulting vector. So the linear combination of U and V with coefficient minus 1/2 and minus 1/3. So, and you see that we can obtain each vector of the entire plane, which contains our vector U and V, by means of linear combinations. And so we can say that these two vectors generate the entire plane they belong to. And now we can generalize the concept of linear combinations to any Rn. So we know what it means to scale a vector. It means to multiply all the coordinates of the vector by the scalar. And now if we add alpha v and b and beta u, we get a linear combination of the two vectors. So we simply take the first coordinate plus the first, the second plus the second, and so on and so on. So this is the linear combination of two vectors in Rn. And generally, if you take n vectors u1, u2 until un, and n scalars alpha 1, alpha 2 until alpha n, then such a sum is also a linear combination of these vectors. So you should understand that this term of linear combination is not in any way restricted to two vectors and two scalars. It can be any number of vectors and the same number of scalars. And now I will show you an example, well, in R4. So let's have a look here. I have prepared three vectors, u, v, and w, and these are vectors in R4. How do I see this? Well, all those vectors have 1, 2, 3, 4 coordinates. So this is how I see that they are elements of R4. And my scalars are alpha equal to 2, beta equal to 3, and gamma equal to -1. So now I will show you how to compute the linear combination alpha u plus beta v plus gamma w. What is alpha? Alpha is 2, u is 1, 0, 2, -3. So now I am done with this first term, alpha u. Then I have to add beta. Beta is equal to 3 times vector v. Vector v is 2, 1, 0, 0. And at the end I have to add gamma w. Gamma is equal to -1, so it will be minus vector w. It is 0, 0, 1, 0. And now I'm actually almost done. I can perform such a intermediate step where I simply compute the scalings of my vectors. So first, you know, scaling of vectors is computed in this way, that you multiply all the components or all the coordinates of the vector with the scalar. So 2 times vector u has coordinates 2, 0, 4, -6. Then I have to scale v with the scalar 3. So it will be 3 times 2 is 6, 3 times 1 is 3, and then 2 zeros. And well, I have to, I can write add 0, 0, -1, 0. So you see what I have done here. I have multiplied all the components of the last vector with -1, and well, these zeros do not affect at all by the multiplication by -1, of course, and 1 is becoming -1. And now it's just vector addition, right? And how you perform vector addition? Well, the sum of 3 vectors from R4 will be another vector of R4, obviously. So I have to prepare place for 1, 2, 3, 4 coordinates. And now the first one is the sum of the first coordinates of the vectors which are to be added. So it is 2 plus 6 plus 0. It is 8. The next coordinate is the sum of the second coordinates of all the vectors which are going to be added. So it is 0 plus 3 plus 0. It is 3. The next one will be the sum of the third coordinates. It is 4 plus 0 plus -1. 4 minus 1 is equal to 3. And the last one is -6 plus 0 plus 0. It is -6. So here you see I have obtained the linear combination of vectors u, v, and w with scalars 2, 3, and -1 to be this vector. And it is, of course, a vector in R4. So now you have seen an example, and now it should be clear to you that you can take any number of vectors and, well, the same number of scalars, and you can by this, in this way, produce a linear combination of these vectors. And well, all these vectors must, of course, belong to the same space. So in this case, in our example, they all belonged to R4, so all the vectors must have the same number of coordinates, otherwise we are not able to add them. And the resulting vector, this linear combination, is a vector of the same kind, meaning belonging to the same space. Now I will show you some very important vectors which will play a very important role in the rest of the course. These are the vectors I'm talking about, this green one and this blue one. This green one has coordinates 1, 0, because, well, it gets delta x equal to +1 and delta y equal to 0, because it's a horizontal vector. And this vector has really a lot of different names. Sometimes it's called I, and you can either write a letter I with an arrow or a fat I, or it is called E1, and it's simply the unit vector in the x direction. And this blue one is the unit vector in y direction. It has coordinates 0, 1, because, well, 0 because there is no change in the x direction. We are going straight up. One step up means that the coordinate y is equal to 1 + 1. And this vector is called j, so you can either write j with an arrow or fat j, or you can call it E2, fat letter E, or E2 with an arrow. And what is so special with these two vectors? Well, they are unit vectors in the direction of the axis, and each vector in the plane is a linear combination of I and j. So take any point, so for example point B with coordinates 5, 1. 5, 1 is 5 times our vector I plus 1 time our vector j. So it is this linear combination of I and j, so it will always be just the coordinates here, which will be the coefficients from the linear combination. And any other point, for example, -5, 3, is the combination of I and j with coefficients -5 and 3, simply the coordinates. Why? Because we this rectangle here, this rectangle with the diagonal being our vector -5, 3, is of course a parallelogram with sides. The first one is the 5 units to the left of our vector I, and the second side is 3 units up, 3 units up. Also, it means 3 times the unit vector in the y direction. And here, for example, point 2 or vector 2 minus 2 is exactly the same linear combination of I and j. And the same situation in the 3 space, but there we have 3 unit vectors. We have unit vectors I will go back to this previous slide. Here I have unit vector in x direction, unit vector in y direction, and unit vector in z direction. And they are called I and j exactly as in the plane, but for the vectors I and j we have z coordinate equal to 0, because these are the unit vector along the axis, x-axis and y-axis, in the plane where z is equal to 0. So here is our vector I, here is our vector j, and here is our vector k, which is going straight up, 1 step up, so it has coordinates 0, 0, 1. So you see, all those unit vectors in the direction with the axis have just one time coordinate 1, and the rest are zeros. And 1 is always standing on the place, on the place corresponding to the coordinate axis along which this vector is running, the direction of which it is showing. And again, each vector in the free space is a linear combination of the 3 unit vectors. And the same principle as in the plane, the coefficients to the linear combinations are just the coordinates of the vectors. So this is just the meaning of coordinates, being a linear combination of those vectors generating the space. And you can generalize this concept of unit vectors to the space Rn, but there again without geometrical interpretation. So you have n unit vectors, and all of them have almost all coordinates equal to 0 and just one coordinate equal to 1. One on the first place, on the second, on the third, and so on on the last. So each of these n vectors are unit vectors in the direction of some coordinate axis. And each vector then with these coordinates is a linear combination of the vectors. Here should be plus. And now, the last thing I wanted to tell you in this lecture, linear combination, this concept, can be applied to any mathematical objects which can be added and scaled. So, for example, this kind of number is a linear combination of numbers x1, x2, up to xn. And you can actually treat real numbers as vectors, but there you take just one coordinate axis with 0 on it and the unit 1. So for example, if you want to depict, if you want to illustrate the subtraction 6 minus 8 is equal to minus 2, you represent the number 6 as a vector, position vector starting in 0 and ending in 6. 1, 2, 3, 4, 5, 6. 6 steps to the right corresponds to plus 6. And well, it's just delta x because we have no y-axis, right? And vector minus 8, if you have to subtract vector 8 from vector 6, you just put the starting point of the new vector where the first vector ended, and then you go 8 steps to the left, and you arrive at minus 2. So this is just another way of looking at subtraction and addition of integers. It's maybe easier to understand if you look at vectors. So this is a linear combination of numbers also, right? You can also have linear combinations of functions. So you see here we have functions sine x and cosine x, and we have scalars 3 and minus 2. So this new function is a linear combination of our two old functions, sine and cosine. And you can see it on the graph. This red one is a curve corresponding to the cosine function, and this blue one is sine function. And this orange one corresponds to this linear combination of two functions, sine x and cosine x, with coefficient plus 3 and minus 2. So the concept of linear combinations is actually quite broad. You can make a linear combination of anything what can be added and scaled. It's not reserved for geometrical vectors. Thank you for watching. Bye bye.